Like, what makes something an exponential?
It keeps going.
It keeps going, so that's the graph, right? It goes up really, really quickly, right? But for the equation, how do I tell if the equation is an exponential?
It has an exponent.
Well, x squared has an exponent. That's not an exponential, that's a quadratic.
Huh.
It has an A value?
Different graphs can have A values. I mean, Michael is on the right track. It has something to do with the exponent.
It's like a variable to the power of another variable.
Not quite. Close.
Variable is a fraction.
Yeah, so a to the x or b to the x, but a or b is just going to be a number, right? So where is the variable?
Oh,
The exponent. So for your exponential functions, we are looking at some number raised to a variable. So like an example would be if we had, say, y equals 10 to the x, or f of x equals 5 to the x. Those would be exponentials because my exponent is in, or has the variable in it. Are we all okay with that? But, like somebody said, what do these graphs do? Or why, like what's different about them? They continue, but how do they continue? Do they like go up really slowly?
like steep.
No, they go up really, really fast. They're very, very steep. Okay. So if we wanted to look at our graph, notice that, like I said, this b value can be anything. So that means that our parent graphs are slightly different, but they're all going to have the basic same shape. So in this case, what is our base? 3. 3 is acting as the b value, okay, or your base value. And if I wanted to make a table, what would be some numbers that I could plug in? Okay, 1, 2, what? 0, -1, -2, right? Now, let's start at 0. If we plug in 0, anything to the 0 power gives us 1. Okay, if I have 3 to the first, that gives us 3. 3 squared gives us 9. But then with our negative numbers, what happens with those?
It's like 1 over.
It flips them and turns them into a fraction. So what would 3 to the negative second be? 1/9, right? So if we graph this, so we have 0, 1, 9. This is 1/3, 1/9. So like we said earlier, my right side of the graph is getting bigger and bigger and bigger really, really quickly. And the bigger that our base is, the quicker that it's going to get big. Okay. Now, what's happening on the left side of my graph, though?
Exponential decretion.
Okay. So as I get more and more negative numbers, okay, like if I plugged in -10, what type of number would that give me? It's very small. But very small what? Is it a very small negative number? Is it a very small fraction or really small decimal, right? So what are we getting closer and closer to?
0.
0. Is there a number that I can plug in for x that would give me 0?
I don't think so. To the 0 power? No.
So anything to the 0 power gives me 1, right? Negative 0? No, not quite. So is there anything? I could get really, really close, right? I could plug in -100 and get a really, really, really small decimal. But is there anything that I could plug in that would give me 0?
No.
No. So if I'm getting really, really close, but we can't get to 0, what is that called? An asymptote. So we have an asymptote at 0, which is why we have an asymptote there, is because there's not anything that we can plug in to our function that would give us 0. So if we wanted to label this line, what is that? No, like what is the equation of that line? Y equals 0 is our horizontal asymptote. Are we all okay with that? Now, what would the domain of that graph be? All real numbers. So negative infinity to positive infinity. What about our range? Okay, so 0 to positive infinity. But can we equal 0?
No.
So what do we have to put?
A bracket.
No. Opposite. Parentheses. If it's a hard bracket, that means that it can equal that. In this case, we can't equal 0. So it gets a parentheses. Or you could say y is greater than 0. But no equal to bar. Questions on that? We're okay with our parent graph. Now, most of the time, are we just going to be graphing our parent graph? Or do we do other things to our parent graph? Yes. What are those called? Transformations. Robots in disguise. Did any of y'all ever watch that? Transformers? It was a cartoon. It was like the little robots that transformed into like cars or trucks or things like that. And that was like their slogan, Transformers, robots in disguise. So that's what I think.
I've never heard of this. Children at one point? I can't tell you.
Shame on you, no wonder you broke a square.
I really can't.
So here are our transformations for our exponentials. And they should look really, really familiar because they're the same transformations that we've looked at in Algebra 1 with our linear stuff, in Algebra 2 with all the graphs that we did, when we did our piecewise project, all of those transformations, same stuff. So remember that this time the inside is a little bit different because like before it was like the inside of the square root or the inside of the square or the inside of the absolute value. This one is technically inside when it's in the exponent with the x. So notice that my h is what moves it left and right and it's in the exponent. Okay, but it still works the same way that it's the opposite direction of the sign. So like if we have -2, it would move it to the right 2 spots. We have +2, it would move it to the left 2 spots. The plus k on the outside is still what moves it up and down. And then the a value on the front is still what's going to stretch or compress it towards or away from our x-axis. But then remember, if it's negative, what happens? Yes, it goes down because it's reflected across our x-axis. So it would point down instead of up.
How do you flip it the other way again?
You would put a negative in the exponent. So like you would have b to the negative x. And that would reflect it across your y-axis. No, it's going up and to the right.
Oh, yeah.
Because it's increasing. So what's another word for increasing? Yes. Rising, okay. We were talking about like real world applications. What would we call it? growing. So remember that these are called our exponential growth graphs. Growth. Can anyone give me an example of something that would use an exponential growth graph? Michael?
Bacteria.
Bacteria. Anything else? Like population, especially like rabbit reproduction, right? They like reproduce really, really quickly. Let's see. You could also do like the first 6 months sales of like the new iPhone, right? Like those would be exponentially. The number of views on Netflix during the pandemic, right? Like that would definitely be increasing. So things that are growing very quickly. Right, so let's look at an example with our graph. So like I said, because each of our bases is going to be slightly different, we're going to start by looking at just the parent function first. So that's just with the base. And we're going to plot some points. Now, we plugged in a couple of different values for this first one that we did, but really, these 3 values in the middle are going to be our key values. That's what we want to plug in every single time, because that's going to give us the general shape of our graph. So if I plug in -1, what do we get out? 1/5, because it would make it into a fraction. If I plug in 0, what would I get? 1. And if I plug in 1, 5. So I'm going to plot those points. So that's what our graph would look like. And that's my parent function, yes? Now, is there anything else going on with this graph? There's a number in my exponent, which is our h value. So what does that do?
It moves it to the
Left or right, and in this case, it'll move it to the right 2 spots. But then what else do we have happening? It's being reflected, because it's negative. And it's being compressed, because I'm going to get smaller numbers, right? So we want to look at the a value first, because that's going to affect the shape of the graph. And then we can just move that graph left, right, up, down, wherever we need to go. Okay, so if I looked at just the a value, so -1/2 times 5 to the x, okay? Could I rewrite that as -5/2 to the x power? And combine them?
No.
Why not?
Because exponent comes first in PEMDAS.
Correct. So in our order of operations, or PEMDAS, exponents have to go first. But do we know what our exponent is? No. So we can't perform that. So then we can't continue to do the multiplication. The only way you'd be able to combine them is if your -1/2 was also to the power of x. Does that make sense? Otherwise, we just have to leave it like that. So if I were to make a chart now for these numbers, okay, does the -1/2 affect what I'm plugging in? No, I'm still going to plug in -1, 0, and 1. Okay, but does it affect my outputs? Yeah, how does it affect my outputs? Yeah, it's going to make them negative and then take half of them because I'm going to be multiplying by a half. So we would get -1/10, -1/2, and -5/2. So now, if we graph that one, so we would look like that. So notice that it has reflected it, so it's pointing down, and it's also compressed it, so it's pointing towards my x-axis. So is that my final graph? No. What do we need to do then?
Move it to the right.
move each of my points to the right. How many spots? 2. Now, do we still have a horizontal asymptote? Yes. Is that horizontal asymptote still at 0? Yes. Because just because we moved everything left and right, well, I have a line. Even if I move the line to the left or to the right, that doesn't affect where the line is at. Yes? So, our domain is what for this graph? Yeah, so it doesn't change. So we would say all real numbers. And we still have a range that is around 0 because our asymptote didn't change. But what did change? The direction. So we're pointing down this time, right? So remember before we said 0 to infinity because we were pointing up. And so we could be all the numbers above 0. But now my red graph is my final graph. If we're pointing down, we can be all the numbers negative or below 0, right? So you would say y is less than 0. So how would I write that out in interval notation? Negative infinity to 0, and we get a parentheses because we can't equal 0. That's where our asymptote is.
Yeah.
Questions on that? Yes.
Why did you shift it right?
Because I have a -2 in my exponent. And if there's a number in my exponent, that goes left or right. And remember, it's the opposite direction of the sign. So it's -2, so I move 2 to the right. Other questions? So this is an exponential growth graph. What would the opposite be? Exponential decay graph. Now, how do we get a decay graph?
That's in negative.
It's not negative.
It goes up on the left
Like
and down on the right.
Put a negative on
It is a fraction. And it's a fraction as our base. Now, it's not just a fraction, though, because technically if I had 5/2 to the x, that would still be a growth graph because it would be bigger than 1. So it's when it's smaller than 1. So 1/2, 1/3, 2/3. All of those would be exponential decay graphs. And why do we say it's decaying?
Going down.
It's going down, which would also be called decreasing. So what are some real world examples of decay graphs? Death. Yep. Super positive one. Other things? Deforestation, right? The amount of trees that you have left. The supply of natural resources that you have left.
Also population.
Population. So if you have like a limiting factor, like if you have a population of deer and it's deer season, population's probably going to be decreasing pretty quickly.
mental health through the school year.
Yes, if you were able to measure mental health, probably that would be one. You could also do like the amount of like metal you have that's being eaten away by like rust. Yes. So we need to start thinking about some practical applications, either with exponential growth or exponential decay, because that's what our group project is going to be over next week. Is be coming up with a real world application.
Group projects?
Yes. I will be picking your groups.
Ouch.
I've been teaching too long to make that mistake again.
What was happening?
But I will tell you though, be careful about the group project because all of my group projects you will be filling out an evaluation form of all of your group members. So if you get a really bad evaluation from all of your group members, you will have a makeup assignment because you did not participate the first time. So you're not going to get the credit for what you didn't do. Now, does that mean you have to know everything about the entire project and how to do it? No. That just means you need to be actively involved in the project. Does that make sense? So if I wanted to make a chart for this one so that we could graph our decay graph, again, we're going to stick with those same 3 key values. So when I plug in 0, what do we get? We still get 1. What do I get when I plug in 1 this time? So I have 1/3 to the first, which gives us just 1/3. But now when I have 1/3 to the negative, what does that do? Yeah, we would have a fraction within a fraction, so we would multiply by the reciprocal, which gives us 3. Which is why now, as we get more and more negative, it's going to get bigger and bigger and bigger on the left. And as we go to the right, we're going to get smaller and smaller fractions. Is there anything that I could plug into this graph that would give me 0? No. So we still have a what? We still have a horizontal asymptote at y equals 0. Our domain doesn't change because I can still plug in any number. And my range is still going up. My y values are still getting higher and higher on the left side, so it's still 0 to infinity. It's just decreasing this time instead. So do all the transformations still work the same way? Left, right, up, down, stretch, compress. Yeah, the only difference is what type of graph you're starting with this time. So in general, you don't need to write all this down. It's just giving you an example. So this is our decay graph. It is continuous. It is decreasing. Like we said, our domain is all real numbers. Our range is all the positive numbers. We still have an intercept at 0, 1. Okay. So in your groups, I want you to start with your parent graph on this one and graph our transformation.
Would it be negative? Or negative? Yeah. The bottom one is the one that is like my friend. Yeah. Yeah, so you can.
Junior was just said
Oh, I'm sorry. Wait, I didn't. Because you have to do the A value, so you have to multiply it. Okay.
So what happens when we take these graphs?
-3.
X equals the same thing. Why is it?
Alright, so I think a lot of us got our parent function, it looks like. So we could graph our 1/4, and that's just going to be at kind of like our normal shape. But then we still have to multiply it by 2. So that's going to stretch us and make it bigger. And this is the graph that we want to use to move left, right, or up or down. So based upon what we're given, what do we need to do? Which directions do we need to go?
Down.
So I'm going to go left 2 and down 3 for each of the points that we have.
I got Y. I got Y.
Oh, yeah, no.
So notice, okay, if I've moved my graph down 3, does that move everything down 3?
Yeah.
So what does that also include? My asymptote. So where is our asymptote now at? -3. What -3? Y equals -3 would now be our new asymptote. But what's our domain this time? Still all real numbers. All of our exponentials are going to have a domain of all real numbers. But now what's happened for our range? It's changed to be what?
To be in
So you want to put your smaller number first.
Oh, yeah.
So -3 to infinity, right? Because basically it would be y is greater than -3 this time instead of 0. Because we've shifted everything down. Questions on that one?